All right, then I guess we can get started. So our speaker for this week is Qianshu. She was Matt Reese's student and just recently started at NYU. And now she'll tell us about that.
Thank you. Thank you very much for having me. Today, I will be discussing some tension between having high quality QCD axion with having a viable cosmology that we think has been a little overlooked in the literature. In particular, I will show that demanding a high quality QCD axion seems to imply production of unconventional topological defects, which is particularly important in the context of post-inflation QCD axion, where we demand axion to be the dark matter, because to calculate the axion dark matter abundance, it is important that we understand the property of the topological defects, which I'll make clear of all those sentences in a moment. This is work I did with Matt Reese and Qianshu, and Qianshu is a grad student at MIT. All right, just to start, aligning the introduction of the strong CP problem, which I'm sure everyone is familiar with. So the strong CP problem refers to the two possible CP violations in the quark sector of the standard model. The first is the complex space in the CKM mixing matrix, and the second is the topological Sator term that's in front of the GG dual. And the strong CP problem simply refers to the fact that experimentally we have a measurement of the CKM phase, which is order 1, and experimentally we have an upper bound of the Sator parameter, which is less than 10 to the minus 10. And the strong CP problem simply refers to the huge hierarchy between these two parameters. There are several important properties of this Sator parameter, which I will be using over and over again in my talk. The first is that Sator itself is actually not the physical parameter. We should be really, because by chiral, if you do a chiral rotation on the quarks, by the chiral anomaly, there will be the phase of the chiral rotation is going to move into the Sator term. So really the physical observable is the Sator bar variable. And another property is that this parameter Sator is 2-pi periodic. So because so the Lagrangian is clearly not going to be invariant when you shift Sator by 2-pi, but because integral of trace GG dual in this normalization integrates to integer, so the action is going to shift by 2-pi n times I, which is 1. So the action is going to be invariant when you shift Sator by 2-pi. So of course, with the axion solution, we're going to have a lot more things in front of GG dual. That's not just Sator. So the important thing is that whatever that's sitting in front of this whole thing needs to be 2-pi periodic, or it is 2-pi periodic. Okay. So I already mentioned axion, but what is the axion solution to the strong CP problem? The solution at its minimal ingredient says that we demand that there is a 2-pi periodic scalar Sator A with a continuous shift symmetry, U1 Pecci-Quinn, that is only broken by coupling between the scalar with the gluon. So now instead of this, just this static parameter in the theory, now I have a dynamical degree of freedom that's also coupling to GG dual. And again, notice that I have put some capital N in front of the scalar, and N here has to be integer, since Sator A, I'm demanding it to be 2-pi periodic. So for the action to be invariant under this 2-pi periodicity, the coupling with GG dual needs to be an integer. Okay. Now, how is this a solution to the strong CP problem? The reason is that once we go through the QCD phase transition, the strong dynamics is going to turn this GG dual term into a potential for our dynamical degree of freedom, which has a minimum that cancels the CP violating effect from Sator bar. Essentially, the axion is getting a VAV that makes the theory in the IR look CP even. Okay. So what we observe experimentally is really the combination of the VAV with the original parameter in the theory. So even though the parameter in the theory is order 1, we are not going to observe the CP violating effect in IR observables, such as the Newfound DM. Now here, if you look at this form of this potential, you'll notice that whatever integer I have sticking in my theory simply is really just counting the number of hills in the cosine potential of my axion. So this n will be very important for us. And so far, it just means the number of hills in my cosine potential for the axion. Okay, so for the rest of my talk, I first want to explain the difference between what it means to have pre and post-inflation QCD axion, and why is the difference so important in the context of QCD axion, axion dark matter, because I'm clearly focusing on one of them instead of the other. I'll briefly introduce the quality problem, which is another ingredient of our talk. Then I will go into the actual physics story, where essentially solving the quality problem seems to imply an unconventional cosmology for our post-inflation QCD axion. I'm going to define or explain unconventional as I go on. So there are two parts to the story. First, I'm going to focus on the skeleton, which essentially we just impose as a solution to the quality problem. We're going to impose the simplest thing we can do, which is some discrete ZP symmetry. I call this the skeleton because really all the model buildings in the literature, still you can embed the ZP into different kinds of continuous gauge group, but a lot of the essential physics is contained in this ZP solution, and we'll be able to learn most of our physics lesson from this. So even though I say it's part one, part two, but I'm actually going to focus a lot of time on this. Then having learned the skeleton, I will go into possible embeddings of the ZP in more complicated gauge groups, as have been done by people in the literature. All right. Okay, what is the difference between pre and post-inflation QCD axion, and why am I focusing on one of them? In four-dimensional models, we can, so I said the axion solution relies on the existence of this theta A. How do we get it? We get it from, as the non-Boson boson of a spontaneously broken U1 Pechenko symmetry at some scale Fa. I'm going to refer to some minimal model of realizing this, where we simply have one complex scalar that is charged 1 under the U1 Pechenko symmetry that gets a bed from something like a 1 bottle potential, and the complex scalar phi has coupling to some heavy quarks. And the phase of the complex scalar is exactly satisfy the criteria for being an axion, because the mixed anomaly between U1 Pechenko and SU3 color leads to theta A coupling to gluon. So this is a very simple construction of the axion solution dimension. Now in this, depending on by pre and post-inflationary QCD axion, I'm simply referring to when the spontaneous breaking of U1 Pechenko happens, whether it happens before or after inflation. Now let's first briefly talk about the case where the symmetry breaking happens before inflation. Now, if the symmetry breaking happens before inflation, and let's keep in mind our minimal model, where the complex scalar just has a 1 potential, it means that the whatever Hubble patch that forms during inflation that formed all of our universe, as inflation mechanism does, is going to have one value of the axion field. Right? Different Hubble patches during inflation will have different axion value, because the axion value is just chosen randomly at the time of phase transition. But by nature of the inflation mechanism, we live in one of those patches, therefore we have one value. That is completely fine, except that we really don't have any way to predict what this value is, okay? Because it was chosen by random. Okay, so what happens when our universe is entirely made of this one value of the axion? Now, at the QCD phase transition, which probably happened long after inflation ended, as I said, the QCD phase transition is going to generate a potential cosine-like potential for the axion. The axion was initially sitting here with a single value, but because of this generation of the potential, it's now going to coherently oscillate around the minimum with the initial amplitude determined by its initial value. And this coherent oscillation makes axion fluid behaves like matter. Now, to calculate dark matter abundance, clearly you need to know what the initial amplitude of the axion is. And like I said, there's just no way for us to predict what that is. So you can demand, for example, the initial axion amplitude is 1. Then to get the correct dark matter abundance, you need Fa to be 10 to the 11 GeV, for example. But theta A could have been a half, and Fa will change a bit, and we just simply don't have predicted power because we don't know what the initial amplitude of the axion is. Now the story is completely different for post-inflation axion. For post-inflation axion, it means that the Pechenko phase transition happened after inflation. So there is a period between inflation and the phase transition, and the Pechenko phase transition, where the temperature is greater than the symmetry breaking scale. So the symmetry is restored. So we have some symmetry restored potential, and axion is sitting in the middle. Now, at the temperature below the phase transition scale, the symmetry is now broken, but the axion is going to fall from the middle to different parts of the universe. And like I said, at the phase transition, different patches are going to fall into different points on the circle randomly. But the difference now is that we're going to see all those patches. So from our perspective, the axion field value is essentially a uniform distribution from 0 to 2 pi after the Hitchcock phase transition. Okay. Now this also leads to the creation of topological defects called the cosmic string, where it, like the name says, is a string-like object where as you go around the string in space, you're winding around the axion value from 0 to 2. Now that is after the Pettit-Queen phase transition. Now we have the QCD phase transition. Again, it generates a cosine-like potential for the axion. But now remember that we already produced the cosmic string objects after the Pettit-Queen phase transition, where as you go around the string, you're going in axion field value from 0 to 2 pi. But now with this potential, what it means is that as you go around the string, you necessarily have to climb up the hills in the potential. So you will be creating, or the universe will create domain walls that grows out of the string. And here, clearly, number of domain walls that grows on each axion string is directly the number of hills in my axion potential, yes.
Possibly a very naive question, but before the QCD phase transition,
Yeah.
presumably instantons can contribute to axion potential.
Instantons, sure.
At high temperature, they're instantons, small instantons.
Uh-huh.
And they contribute to instant potential? No, not they instant potential.
Sorry, the usual calculation, the instanton, let me see.
At high temperatures, instanton calculations are under control.
No, but you see, of course, small instances still exist, but QCD is in the deconfined phase. And so there is no vacuum expectation value of G mu squared, and therefore no bias, no ethers, and
Why
therefore.
do you think there's a potential? Why isn't it already seen before?
You see, it is known if you want to calculate G mu squared, it is known you have to have already split between eta prime and the rest of the Schrödinger forces. If you have no split, at least in the chiral theory, you can show that G mu squared has zero expectation value.
Maybe I'll ask you more about that later.
Okay,
A bit possible.
okay.
That's okay. Just that you haven't educated. Please go ahead.
Thank you. Right, so the number of the capital N, I have been calling the number of hills in the potential, is now the number of domain walls that attach to each cosmic string. And the cosmology is very different depending on whether NDW is 1 or not 1. The reason is that when NDW is greater than 1, the string wall network is going to be stable because each string is going to connect to more than one domain wall. And once the domain wall meets another string, it's going to produce more domain walls. So this whole network has an infinite extent with no boundary, and there's no way for it to collapse. And long-lived domain wall is very bad for cosmology because they have a huge energy density. They're literally very dense sheets of energy density with infinite extent, and they will badly violate standard cosmological observation. Okay, so we cannot have that. Now, when NDW equals to 1, the string wall network can collapse because each wall essentially is now bounded by one string, which can form as a boundary. So when the domain wall tension becomes significant, domain wall will pull the strings towards the center and the whole network will collapse, possibly creating a lot of axions in the process. Okay. Now, in this case, combined with the initial misalignment production, which is the initial uniform distribution of the axion from 0 to 2 pi, and the production of dark matter from the evolution of the cosmic string and the final collapse of the string wall network, the dark matter abundance from post-inflation axion is in principle exactly calculated. So this is the qualitative difference I want to make between pre-inflation and post-inflation axion. I say in principle because this calculation is very difficult, but nonetheless, in post-inflation axion, the dark matter abundance does not rely on some guesses of the initial condition, while for pre-inflation, like I said, your dark matter abundance prediction always depends on what you choose your initial axion amplitude.
Excuse me, go ahead.
Oh, okay, so when people are doing these string calculations and they talk about like scaling solutions and stuff, is that all happening after the QCD phase transition where you have domain walls, or is there stuff happening even before?
Even before, the scaling
Okay.
solution is referring to, so because there's a huge amount of time between the particular phase transition and QCD phase transition. Right, and as well, actually, let me explain now. So the domain wall production happens not only at the collapse, but also during the evolution of the string network. The string is gonna meet each other, cut pieces, cut the long pieces, some long pieces into loops, the loops is gonna radiate axions. So you need to understand all of these. And one of the things that's super important is how many axion strings we expect to have in a Hubble body. And the scaling solution is referring to that, which is super important for dark matter abundance prediction.
Okay,
But that is not once the QCD phase transition happens, the domain wall form, and quite quickly the whole network just collapses.
even strings that are separated by more than a Hubble radius?
So usually, the domain wall is going to, usually the scaling solution says there is about some order one number of strings in a Hubble patch. And the domain walls are bounded by the string. Right? So the string is enough to form a boundary for the domain wall, and the domain wall will fill.
Oh, okay, but it's still contained in one Hubble.
Yes.
Oh.
Excuse me.
Yes, sorry.
May I ask a question?
Yeah.
This process of, let's say n equal to 1.
Yes.
But this process of annihilation, the wall between two strings, and this also strings will simultaneously annihilate each other, right?
Yes.
First of all, it's not doesn't happen immediately, right?
Not immediately.
And then there is some energy release
Yes.
in the process.
Yes.
Should we be able to see some consequence of this very huge energy release?
So let me see, you're saying it's huge because,
Because the size of the object is, as you mentioned, it's a order of the Hubble
yes,
size, right? So although tension is pretty small,
yes,
but the size is pretty huge, right?
yeah,
It's big.
Huh?
Why is the tension small?
tension is the QCD phase transitions, yeah.
Okay, but
Yeah, well, it's not as small, but it's smaller because the quarks are pretty light, right? So
Actually,
the tension is smaller than naive, but it's not as small as the size is large.
right, so the network is going to collapse as soon as my domain wall tension, with some wall pancake of radius r, I have a string tension and I have a domain wall tension. As soon as my domain wall tension, the size of the pancake is such that the size is on the same order as the ratio of the tension, because the ratio of the string tension and domain wall tension differ by 1 unit. Then the pancake is going to collapse. So it's not, they're not going to survive.
Not like that, because what happens first, under your condition, there a hole appears through tunneling, right? Because it's through bubble formation on the domain wall. Bubble means, I don't know, pancakes formation of the holes in the domain wall, and then this holes start expanding like crazy, and eventually the entire energy which resided in the domain wall, it's expanded, it's spreads out over the space, at least at first some, maybe at first near this hole, but eventually, so I think it's like an explosion in this space. Right?
So yes, if the domain wall annihilates by tunneling a string loop, it will be too slow. So I'm actually demanding that before the domain wall formed, my universe is filled with NDW equals to 1 string.
Yes.
Does form a skeleton where the domain wall is just gonna fill up the boundary. So the boundary of the domain wall is already there. And at the QCD phase transition, it simply fills in between the string. So I'm not trying to nucleate a string loop on the domain wall, because that would be very slow, right?
So you say that the whole remnant of this will disappear before QCD phase transition, right?
Well, I need QCD phase transition for the domain wall to form, but without the potential, there will be no domain wall in the first place.
Okay, so let's speak about the decay of these three domain walls after QCD phase transition. But
Yeah.
QCD already establishes itself as QCD, right?
Yeah,
Then you are not right, the decay will be fraternity.
it's not bipolar.
Huh?
It's not bipolar.
Why?
Oh, because, sorry, the strings exist and the domain walls fills in between the strings. So
Yeah,
they-
but strings are very far apart from each other, right? You said one string and then another one at, let's say, 1/2 of the Hubble distance.
Right.
So even with the tension, if you want to annihilate the whole wall, especially classically, you have to, for the strings to migrate in the space and come close to each other.
Yes, they do. But as the,
And at
as
this
the,
point,
Mhm.
along this line where they collapse, there will be a huge energy because strings are very fast, will be very fast.
For instance,
At
like
this point.
you actually produce axions, like
You
axions
predict axions,
from
yes.
strings, right? So a remnant of this actually does matter. So for instance, diagonal rate and balance computation, they included axion production out of this string annotation.
they,
So in a sense, like you two have, yeah.
yes, but it's definitely not distorting the background cosmology, but yes, sorry, perhaps I was not clear. It will contribute to the final dark matter, axion dark matter bubbles.
Okay, so you say that this process produces dark matter.
Yes,
And it's, I mean, the axiom produced should be not low energetic numerically, right? Because they collect into themselves all energy which was originally in the strings and in the domain.
right, but this is not the only part, so axion dark matter is not completely produced by the final collapse. Like I said, there's a huge amount of time between Higgs phase transition and QCD phase transition, where it's just the axion string kind of cutting itself, wiggling and radiating axion.
Yeah.
And those are not really non-relativistic.
This are very slow, yes, I
Yeah.
agree with it.
So yes, there will be some, potentially some higher energy, non-relativistic axion, but it's not going to make, for example, dark matter hot.
Okay.
Yeah.
Okay, thank you.
Where was it? Yes, so like I said, for post-inflation QCD axion, the dark matter abundance is in principle exactly calculable. So people have invested computational resource to do high resolution simulation of NDW equal to 1 axion, and in particular using the minimal model, where your axion is just a phase of a complex scalar charged under U1 Cauchy plane. And they get very precise prediction of the axion mass, which they should, like I said, in principle, since the whole thing is exactly calculable, there is only one axion mass that really gives the correct dark matter abundance. So for example, from this collaboration, they predict the axion mass to be this value, which kind of sits here in the MA and GA gamma gamma plane, and it corresponds to FA approximately 10 to the 10 to 10 to 11 G. So today, I'm not going to be talking about the difficulty of doing this kind of simulations or systematics of these simulations. On the other hand, the point I want to make is that, of course, if I may speak for the people who did the simulation, probably nobody is claiming that the minimal model is the correct axion model. Okay? They choose something that is easy to work with. But now I'm going to say that if you want to have a high quality QCD axion, the minimal model is probably not even a good approximation of how the topological defect should behave in the early universe. Okay? And that is what I'm going to argue in the rest of my talk. Sorry, this is a lot of things I have already said. The simulation shows that axion production is dominated by topological defects, like we have been discussing a lot. So predicting of MA really requires understanding of the defect evolution, but the quality problem kind of suggests, we think, non-minimal model or cosmology or defect. And I will explain what the non-minimal
So this
Yes,
also kind of maybe related to the quality problem. So you said like if the domain wall number is larger than one, then we have the domain wall problem. But people usually you can just put a bias right, to a potential problem. And
yeah, so if you want to put bias, yeah, I will not be talking about the bias solution
I see.
because it is, I mean, in my mind, the bias solution is really being pushed by both sides. I think it only survives in a tiny corner around here, not even by demanding it has the correct dark matter, just by saying that it doesn't overclose the universe. So it already has a very small range of parameter space where it doesn't even violate cosmological observations. Where on the other hand, this is, but having NEW equals to 1 or having the existence of correct string is more like a mechanism instead of adjusting all the. Okay, so what is the quality problem? I've said the word many times, but recall that the axion is a solution to the strong CP problem only if its potential is only generated by the strong mix. Notice that the combination of theta A is already explicitly broken by its coupling to GG table. So it's natural to have in the theory, there's nothing preventing additional breaking of that continuous symmetry to exist. But if the additional breaking is not small, we don't have the correct potential, and the axion is not going to be a solution to the strong CP problem. For example, I think quantum gravity is expected to break all global symmetries. So we at least need to have U1 Pechiquin symmetry breaking operators that's suppressed by M-Planck. Now it turns out that even if your operators are suppressed by M-Planck, because the quality problem is such, because the strong CP problem really needs to get rid of theta to be less than 10 to the minus 10, you need to forbid the existence of these kind of operators to pretty high n. Now the actual value of n depends on FA, but n equals to 10 is some kind of number that is good to keep in mind. So the quality problem simply refers to the fact that we need to forbid shift symmetry breaking operators. Now, so how is the quality problem related
You
to
say you need n greater than 10.
Yeah.
And of course, depends on what the coupling is in front of that.
Oh, I'm
So-
assuming order 1.
Okay, but so just to have an idea, if n is 5, how small does the coupling have to be?
So this is the Fn is 5. The potential is just the FA over 1 5 gets of F, it's FA over M-Planck. And that gives me the mass.
Okay, blank is already 10 to the minus.
Yeah, so I would
7
say
or
you would have to
10
take that
minus
to power of 5, yes.
Mm,
I would think that you would, if you go from 10 to 5, I would think that you would need to dial the coupling by the ratio to the 5.
So you need a coupling 10 to the minus 40 or something.
It's very small.
How is it then spoiled? I guess I'm not seeing exactly, if n is 5, so
Yeah.
just the lowest order non-normalizable coupling. How is it spoiling it, and why does that coupling need to be
Oh,
so small?
yeah, because it's, so if I have 5 to the 5 over M-Planck, phi is going to get Bev, and it has, but phi is going to become Bev times e to the I theta A, where theta A is my axion. And of course, I have a complex conjugate. So summing of it would give me an axion potential, which is where the scale of the potential is given by this operator. It's given by FA to 5 over M-Planck, which is way too big compared to the QCD potential, which is lambda QCD to the 4. Sorry, yeah, the comparison is with lambda QCD to where, yeah, that would happen faster. Yes. So okay, so to solve the axion quality problem, it is natural to resort to some symmetry reasons why these operators are broken. So let's think about the simplest, essentially the simplest solution, which is demanding a ZP symmetry. And now I will explain why the quality problem is becoming related to the cosmology and the domain wall problem of axion, post-inflation QCD axion. Now to forbid operators like phi to the p over M-Planck p minus 4, we can try to make phi shifting by 2 pi over p a gauge symmetry. And this immediately forbids all operator up to power of p. Now, how can we make this partial shift a gauge symmetry? Now, after the ZP symmetry, axion is going to shift by 2 pi over p because it's just the phase of the complex scalar. But recall that the coefficient, so the axion coupling with GG dual must be, the whole thing in front of GG dual must be 2 pi invariant. It's only 2 pi invariant. So if we want it to be invariant under a shift of 2 pi over p, it means that the coefficient in front must be a multiple of p. This is the only way to construct the theory where this partial shift is a safe gauge symmetry. Okay. But here, like I have always said, I will call this integer in front of theta A capital N, and capital N is exactly our domain wall number. So our domain wall number looks like it's S times P, which is of course greater than 1, because we keep saying P needs to be at least 10. So some integer multiplied by P is clearly greater than 1. I'll call this the first pass because this is too naive. Why is this?
So you drop the requirement that you have only one, right? One, and DWV is equal 1. You want to drop it.
Oh, I'm not dropping it. I'm starting from trying to solve the quality problem
Yeah.
to say why that often leads to large NDW. Well, actually, it doesn't give NDW bigger than 1, as I will explain here.
Okay.
Yeah. So naively, my NDW counting gives me S times P, which is bigger than 1. What does NDW equals S times P mean? It means that if I draw the axion potential after QCD phase transition, the neighboring vacua are separated by theta A shifted by 2 pi over SP. That's just the definition. But remember that we have gauged this ZP symmetry. So under the ZP symmetry, theta A is going to shift by 2 pi over P. It means that neighboring vacua are actually gauge equivalent when S equals plus minus 1. I'm not going to, so because we're staying in the IR, making S equals to plus minus 1 is really a UV model building question. But I'm just saying that if you have managed to do that with your model building, then actually your neighboring vacua are gauge equivalent. So what that means is that there exists another state, which I call theta tilde, defined by P times theta A, that is also 2 pi periodic. Okay. So what that means graphically is that here, again, I have my QCD phase transition potential for my theta A, which is a 2 pi periodic variable. But actually there is, since all the vacua are gauge equivalent, I can define another variable theta tilde, which is also 2 pi periodic. But that as theta tilde goes from 0 to 2 pi, it only goes across one hill. Okay. So when you count your domain wall number with respect to this new 2 pi periodic variable, you'll find NDW equals to 1. Okay. Now this is the second pass. There's a final pass. This is often where people end when they claim they have solved the domain wall problem, which is natural because you have found.
Excuse me, do you imply that theta prime enters just in the sum, or how it's done? Let's say you put theta prime equal to arbitrary value and don't change it.
Sorry, can you say that again?
Let's say you put theta prime some vacuum and don't change it in the domain wall, inside the domain wall, but theta changes inside the domain wall. What's your
Outside the domain.
You build domain wall only with regards, only out of epsilon related to theta. Forget about theta prime. Another parameter theta prime, which has another periodicity. But you say it's
But they are. Sorry, I know in the cosmological tension. You will be.
May I ask you, but when you are saying that neighboring vacua are equivalent, right? Then your periodicity should be changed, right?
Sorry, are we? Sorry,
No, I mean,
is the problem that
yeah, you said that neighboring vacua are gauge equivalent, right? Say for S equal 1. But
Yes.
if they're equivalent, then you know, we can kind of redefine what we call theta, because then you know, it's I would say that then you would ask for periodicity, different periodicity, right? I mean, corresponding to this p, or otherwise, what means equivalent? Either there are indeed different, you know, kind of maximum, minimum within a periodicity, or just one segment of theta bar is returning you back.
Right. Okay. So, if it is confusing to call this theta tilde variable also 2 pi periodic, we can say that redefinition is not necessary, because in terms of cosmology, there is a object that tells me how I should count 2 pi, and that is whatever that winds around the cosmic string. So let me perhaps come to the second point, which might make it a bit clearer.
So people often stay here to say NDW equals to 1 and the domain wall problem is solved. And I'm saying that that is not enough to solve the domain wall problem, because remember, and that is related to this periodicity discussion.
But why it would not be periodicity theta plus 2 pi divided by p?
That is fine. We can call it that. For if that's clear, let's stick with calling theta A 2 pi periodic and call theta tilde 2 pi over p periodic. That is fine with me.
But yeah, but hopefully this next point will make it.
Excuse me, do you still have one axion or two?
There's still one axiom.
Yeah, no, but if this equivalence does exist, then counting how many peaks are there seems physically irrelevant, because it's counting how many instantonic transition you had through this barrier. That's it, and it's not like kind of. I mean, okay, it's kind of theoretical counting, but then I mean. And for you, this number n was important, right? Number of this pixels. So in this way, kind of confused. So just not following.
To make it clear, it's not a theoretical counting, because there is a physical object that tells me what I should be counting the 2 pi with respect to, and that is the cosmic string that's being formed at the Paget.
No, but if your periodicity is shorter than 2 pi, then what if your periodicity is not theta plus 2 pi, but theta plus 2 pi divided by p, as you mentioned?
Yes. Yes, for my theta, it does not. What I call the periodicity only matters if I know what is winding around the cosmic string. So here in the minimal model, like I'm trying to show with this wine bottle potential, at the Paget phase transition, we by the Kibble-Zurich mechanism, we know the axion is going to fall to all points on the circle. So this circle is what we need to call 2 pi, because that is what is that is the 2 pi that's winding around the cosmic string.
Okay,
so
but then I would not call that neighboring stuff is gauge equivalent. Then you are not saying that they're equivalent. They are saying not equivalent.
No, they are gauge equivalent. I'm saying that the cosmic string, the string. So in my theory, there exists 2 kinds of string. The first one is the one that's being generated at the Paget phase transition by the Kibble-Zurich mechanism, where my theta A winds by 2 pi. That's just a fact from the fact that I have a wine bottle potential. But because I have gauged ZP, in principle, in the spectrum of my theory, I also have the existence of strings in the spectrum of the theory. Not saying physically existing in the universe, where theta tilde winds by 2 pi, which is partial winding in the perspective of theta A. That string exists. The point I want to make is that both those strings exist in the theory, but only the red one is being generated by cosmology, by cosmological dynamics, by the Kibble-Zurich mechanism. Yeah.
So,
Okay.
because I was thinking that, let's say this Theta tilde.
Yeah.
Is a subset of the other transformation. So I was thinking that the, let's say the new strings, you say, is related to the version of theta tilde, are a subset of the previous strings. Now you say they are different.
I'm saying, oh, you're saying it's subset, right? So, I see. You're saying the red one looks
Yeah.
like a higher winding.
This is what I'm thinking. Yeah, this is what I
I'm saying claiming they're different because I can write down the classical, how should I put this? The global string, the kind of the classical field solution that we know as cosmic string is really only the red one. Like the say the tilde string, they don't exist as, I cannot write it as a profile, some field profile of phi. Because from the perspective of phi, it's not winding around the 2 pi invariants. They exist in theory by some completion, by the completion of the spectrum. That I know the difference between a gauge CP and a global CP. The only difference is the existence of dynamical string-like objects in the spectrum of my theory. But from the cosmological perspective, I have no idea how the strings can be formed. They cannot be formed. And they have a tension that has nothing to do with Pechstein phase transition.
Are you saying that basically these fractional strings?
Yeah.
Are just, their tension is very large, so.
Tension is very large.
Because of that, they're not the ones that are produced.
They're not the ones that are produced, they're not produced by Kibble-Zurich, just by the fact that Kibble-Zurich is by random falling into the vacuum manifold, which is the whole circle. And then they're irrelevant for solving the domain wall problem because their tension is so large, they don't exist individually. So to produce a loop of them is extremely slow. You can quantum produce a loop of them. But
Okay, why don't you then forget about this statement? If they don't participate in anything. Huh?
I understand.
They don't participate in everything, they don't create strings, then ignore them. And then you are back to the situation from which we had from the very beginning.
So,
But you're trying to associate all those different minima to each other through gauging it, right?
yes, and the fact that they're irrelevant is only for the minimal model. So clearly here, we don't have enough circles in something.
So
We have, yeah.
if you would like, maybe not, it wouldn't even do that. I was just thinking, if you were sitting on the top of one of those other periodic bound, not that kind. Because that's a different barrier, right? That's not the same barrier.
That's my one model.
Right,
Yeah.
but now you have along
Oh,
the circle, you
yes,
have
yes,
ups
yes,
and downs,
yes.
right? Right, you have the wiggles, ups and downs.
But the wiggles of ups and downs don't exist when I produce the cosmic string at the Pechstein phase transition. That's why I'm saying that they are
Right,
dynamically
right.
irrelevant
Right,
at that point.
right.
Yeah.
Right, but afterwards, then you have the wiggles.
Afterwards, I will have the wiggles.
And at each one of those dots is a minimum of the wiggles.
Yes, exactly.
Right.
Yes.
And
But
you're trying to use the gauge symmetry to associate one dot with the other.
yes, but unfortunately, at the Pechstein phase transition in this minimal model, I've already produced a bunch of those red strings.
Yeah, the red strings are fine, it's just,
And they're,
why are you even calling them strings associated with the blue, with the dots? Why is that?
oh, there are string-like objects where when you go around, if you
You can
imagine,
go around, here you can go around, but what are you going around?
no, if you imagine, for example, the CP comes from Higgs-in, gauge CP comes from a Higgs.
Oh, okay, so you have another direction, you have this another direction.
Yeah, so yes, actually, perhaps the lesson here is that one circle is too little. I need to have some other continuous, that's why people try to embed CP into more complicated continuous gauge group, where I can make this same relevant. Yes.
Different parameter altogether.
Doesn't have to be, it depends on the embedded. And there is one model.
Right, so I guess, what are you gonna do with this thing? That's,
Okay.
Before moving.
Oh,
to-
yes, yes.
May I ask one
Yeah.
quick question? S is a normal coefficient, original only coefficient, S. And you begin with the assumption that S is plus minus.
Yes.
You go to person, but, and S is denoting the number of gauging column minimum, right?
Oh, P,
So
no.
if you
Oh,
start
yes.
with the assumption that there's only one gauging column, minimum, that there's no domain of problem from the beginning.
No, P is the number of gauge
But
equivalents.
but then you can use gauge columns argument to identify these many different
Yes,
fuels
yeah.
arising due to this CP.
Yes.
But I think that that's irrelevant for domain problem. Domain problem concerns the original numerical question. So if you begin with the S equals -1, then why do they argue they solve?
No, the original anomaly coefficient is S times P.
But P is arising from imposing CP, gauging CP.
Exactly, I'm
And then
saying,
gauging quantity, they're not relevant for domain problem. So I think what really matters for domain problem is S, the number of gauging quantity. But if you start with the S equal ±1,
Yeah.
then why do you, I mean, what do they solve here?
okay,
There's no domain problem.
yeah, I don't think we're necessarily disagreeing, because you see S equals ±1,
So then, if
does
they
give me,
really want to solve domain problem, then they should explain why S is ±1.
they should, and I'm arguing that's not enough.
And for example, for TSFC, what is S? I think it's not.
Oh, actually, well,
Yes,
anomaly
it's not
coefficient is
actually
S.
What?
Yeah, they need to explain why S is 1.
Yeah.
And I'm saying it's not enough. I think
It's
that's
not,
not, it's not
it's
enough.
not enough. Even if ZP is gauge symmetry.
It's not enough because of the difference between the red strings and the black one. The Kibble-Zurich mechanism produced the wrong
Let me
string.
try to explain what could be, how this scenario could be achieved if you try to build a model. We know that the minimal scenario, which is n equal to 1, arises if you have a scalar field, which is the fundamental presentation of the SQL group. But it doesn't have to be the fundamental representation. If you make it in the adjoint or something like that, and then you will have some n, a group coefficient, right? Now, and periodicity will be different, as you understand. Then you have to introduce theta and theta bar, okay? Periodicity in theta will be not the same as in theta bar, because theta from theta bar you will have a different coefficient. The quark, the coefficient is determined by the group coefficient of this triangle graph with a heavy quark, right? And whether it's a joint or fundamental or maybe five, maybe to index some representation, because
But if it's fundamental, like in your model.
now the question is
the number of layers.
Yeah. But what bothers our speaker today, because she wants to discuss domain walls and string, is so far theta are two parameters. One of them becomes dynamical because we call theta, we allow theta to be x-dependent. So in principle, you can have two axions in this model. You have two thetas, you can have two distinct axions. But you may have one if you say theta bar has no, by construction, just a number, has no x-dependent, it's not a field, it's just a parameter. It has no dynamical life of its own. Then whatever is it produced in this, its contribution of this quark, which is not, which phase is not dynamical, is totally irrelevant because it's a value of some parameter at the initial moment of time. It never changes. It cannot wind. It cannot form domain walls. So you have to say how many axions you have in your theory. Okay. If it is one, and if it is associated with the original theta, which appears as a phase of the complex fermion in the fundamental representation, that's the end of the story. You may have many other thetas with whatever periodicity, doesn't, because the only dynamical object is this axion, which builds when it rotates around by pi, builds a string, and strings are the edges of the domain wall. Okay, and only these axions are produced through the collapse of the topological details. Okay, but if you have two axions, one for theta, one for theta, theta twiddle, theta theta, the situation has changed. But you have also two F-pies in this theory, right? Not two F-pies, but two parameters F where you have two U1s which are spontaneously broken. They can be broken at different scales, right? And it may happen that one parameter is broken at very high temperatures, another is broken at temperature below QCD transition. It might happen. So you have this degree of freedom in your head. So I think something of this type is being, but the only thing which I don't understand, axion, is it related to theta or is it related to theta? So because you need n equal to 1, not to proliferate domain walls, which stay in there, you need it related to theta. You need axion related to theta. Then you can forget about your theta bar. It can have whatever periodicity. It's not observable physically.
But
It doesn't have theta bar, doesn't have domain walls at all. And what? Theta is parameter. Theta is a fixed parameter, the way it appeared in the theory. Okay? But your theta bar, because it produces something, let's say it produces equal to something as a parameter. We don't care. Anyway, whatever CP non-invariant terms appear will be screened by this basic epsilon, which you have associated with it. You wrote yourself. If you come back to your first page, there was n theta plus theta bar.
So
theta
bar is constant, but she is referring to theta tilde, which is
Yes,
theta bar.
exactly.
So
That's what I'm saying.
For this is not introduce a subset of all things.
yeah, but so am I correct that you don't discuss like the fate of this red screen?
yeah,
Yeah.
sorry, the phase.
The fate of
But I'm trying to add more or less I think so to the same question. Look, when you discussing this two dependence on this number p, then this symmetry that p, which was introduced, is not a gauge symmetry. So that p is not a gauge symmetry of the theory. So when you are saying that neighboring vacuum, say, gauge equivalent, it does not refer to this structure associated with this, when you divide it by by p different vacuum. So this gauge symmetry, it is associated only with original gauge field, not with not with ZP, right? So ZP, it is if you like, it's not a gauge symmetry, it's a normal symmetry. It's not. It's wrong.
Sorry, it is a gauge symmetry. I can make
It's
this
gauge
by
symmetry.
Higgs.
Yeah.
It is a gauge. I can just make it by Higgsing a gauge U1 with a charge P.
I see.
scalar.
Okay. It's answer my question, right? Because when I ask about equivalence, right, it's only can be when that P is indeed gauge symmetry, right? Yeah.
Yes,
Okay.
ZP. Yes.
No, but if you gauge your U1, then you lose axion.
No, not the U1 pitching plane.
It's different. It's different.
Which one more?
U1 CP is not one patch. This is different U1. It's different.
Different.
It's a different.
But then why do we bother is it is different? Now it's a gauge symmetry.
An example to solve quality problem.
Which problem?
The quality problem.
Excellent quality problem.
I don't see how it's solved. I see the standard minimal construction, whatever you wrote about theta tilde.
Right.
is irrelevant.
Yeah, we don't have to talk about the gauge you want, just the gauge ZP. Sorry.
Yeah, maybe you could
Yeah.
go on. This will
I
this will
have-
become clear.
Yeah, sorry. Sorry. Let's see. Yeah, let me put,
I'm very sorry, so just to summarize, so even if.
sorry, can I ask?
So sorry, so before imposing CP, even if you have a number equal to one, like you still have so you're saying like, after imposing gauge and CP, you have a problem. Which
Yeah.
one?
Yes. Or, yeah, perhaps this slide actually answers some questions, hopefully. So we can solve the quality problem by imposing some gauge symmetry to forbid the U1 breaking operators. Naively, if you impose it to P, you will lead to NDW proportional to P, which is greater than 1, and it's bad. And I'm arguing that counting of domain 1 numbers should be done with respect to the actual string that formed in the early universe. So there is a necessary condition, which is perhaps some of the question, why is it relevant? The necessary condition that you need in your theory, there need to at least be this tilde with the respect to which your domain 1 number is 1. If you cannot find such a theta tilde, there's because the smallest, if the smallest 2-pi periodic variable you can find already has NDW greater than 1, there's no hope to solve the domain 1 problem. But this is only a necessary condition. But the sufficient condition that is much more non-trivial because now it's a dynamic one, and it's often forgotten, is that the correct NDW equals to 1 string actually need to form in the early universe. Because remember, we solved the domain wall problem by having a skeleton form a skeleton of correct strings where the domain wall can end up. If the correct strings are not formed in the early universe, you cannot claim that the domain wall problem is solved. And hopefully I have demonstrated the minimal model that people really spend time to simulate does not satisfy the sufficient condition. By the table-direct mechanism, you form those red strings, which are the wrong string. Okay. So the question is any model that does, and what is the behavior of the strings? Let me just skip to a model in the literature, which we think is the leading contender. It's not guaranteed that they solve the domain wall problem, but we think they have the highest chance. So this is a model where now instead of a gauge ZP, you have a much more complicated gauge symmetry. So we have a gauge SUN that's being spontaneously broken to gauge SON by a 2-index symmetric representation scalar of the SUN, and our axion lives in the phase of that scalar. Okay, so now the scalar is more complicated, but axion is still just a phase. I think I skipped the model, but if you write down the interaction between the phase with the dual, you will get n because your heavy quarks are fundamental representation of SUN. So in the eyes of SU straight color, I have n quarks, and having n quarks coupling to the scalar means that I have n here. But there is, of course, the gauge SUN has a Zn center, and the neighboring vacua are separate. Sorry, here is a bit more complicated. So the neighboring vacua are separated by theta A, shifted by 2 pi over n. If you consider the case of all the n, I said that theta A is the phase of a 2-index symmetric representation of the SUN. Now, 2-index representation under the center of SUN is going to shift by 4 pi over n because it's charged 2 under the Zn center. So what that means is that here, again, I have my axion potential. My operation of the Zn center on the axion is going to shift it by 4 pi over n. So it's not going to go from minima to the neighboring vacua. It's going from minima to 2 over. But of course, you can still try to construct the correct string by doing this operation 3 times. So I have a Z3 operation of the SUN center that goes from here all the way to this minima, but I still have the 2 pi periodicity of theta A that allows me to go back and relate the 2 neighboring vacua. So I guess, again, I have a case where I can identify a theta tilde variable in my theory that goes from neighboring vacua, and it is 2 pi periodic because I can combine all the different symmetries in my theory to make sure the neighboring vacua are gauge equal. But I still have the very important question of does the correct string actually form in the early universe? And from this figure, I hope it's clear that the correct string looks actually quite complicated. It has to be a composite of some string that winds 3 times in the center of my SUN, and also combines
with another string that winds by 2 pi in my theta A. So it's a composite schematically here, shown here, that combines these 3 strings, which has 6 domain walls attached to it, and where 5 of the domain wall ends on my theta A string. And then the whole thing acts like the correct string where only 1 domain wall is coming out. Now, at the time of pitch-between phase transition, we expect all kinds of strings with different domain wall number to form. Right? Remember the Kibble-Zurich mechanism? How does the Kibble-Zurich mechanism produce topological defects? It produces topological defects by letting the phase fall into the vacuum manifold randomly. There's no way for some local minimization of energy to change the winding number of defects. So all different kind of defects are going to form at the phase transition. So the correct string can only form by post-phase transition mergers. And I'm just going to say that we really don't have good analytic nor numerical understanding of mergers of global strings, partly because that global string has divergent tension. So it's hard to even define, if you want to calculate the kinematic constraint of mergers, it's even hard to define the tension of each string property. There's some numerical evidence that mergers do indeed try to minimize the global winding. So there is some hope that the correct NDW was the 1 string form in the early universe, but it is far from clear. So I'm very short of time, let me just skip to the conclusion. I'm very happy to talk about any of this with any of you later. Sorry about this, I'll be very short. Yeah, so in conclusion, I'm focusing in this work, we have focused on the post-inflation QCD Axion because it is a solution to the strong CP problem, and it also has the prospect of uniquely determining predicting the axion mass if axion makes up of dark matter. Now, domain wall problem often plague high quality post-inflation axion models, and people often stop by identifying some periodic variable with respect to which domain wall number equals to 1. I hope I have shown that that is only argued that that is only a necessary condition, and the sufficient condition for producing the correct axion string is very non-trivial, and it's a dynamical question. I did not talk about that at all, but okay, so many remaining questions. Does a viable high-quality post-inflation axion model actually exist? I have tried to highlight that SUN spontaneously to with all them seems to be a leading candidate in the literature, but still the correct string is only going to form by mergers, and so far we really have very poor analytic understanding of these objects. And as I briefly mentioned at the beginning, another thing that's very important for predicting the dark matter abundance is to understand the behavior of the string network all the way from the Petroglyph phase transition down to the phase transition. And in my opinion, it's really not clear at all that this more complicated model is going to produce a string network that have a similar structure as the minimal model that people have been spending a lot of resources to study. Okay, so in conclusion, properties of topological defect from high quality QCD axion is really unlikely to be like the minimal model. And what is the correct axial mass to produce bulk dark matter is still unclear. Thank you.
I have a remark. You have string, anti-string, right?
Yes, yeah, it'd be a boundary.
So you said that the string tension is divergent, but if you have string anti-string,
Yeah,
it's not divergent because it's naturally, there is an opening, but it's cut off by
yes,
between string fees.
yes. But for my purpose, I want to form in the end, what I want is a bunch of axion 1 to 1. So I don't just want them done by mergers. The fact that I want to have axion
But one string, a global string, of course, one string step can diverge. No.
Yeah, so yeah, that's what I mean. I cannot, given that I want global string and I want to form them from mergers, my merger system by definition has non-zero global winding.
So you have to have two in order to your string, your domain will annihilate. You have to have a string somewhere here anti-string somewhere here. There will be the main wall, which is between them. And overall, if you could make a circle as large as this size of the domain wall, including string edges, it's
I'm not talking about the later collapse of the wall strings. I'm
Yeah.
talking about the string-string interaction, like long. I have many different kinds of strings in my universe with different winding of axion on them. I want to make sure in the end I'm left with dominantly winding one string. So I need to understand how strings with different winding meet and connect and merge. And that
but the number of windings, unless you allow tunneling, the number of windings doesn't change. If you created a universe where there is some winding due to this,
locally, yes, globally, it's.
Yeah.
Yes, but locally, for example, in the minimal model, we never have higher winding strings because they split into winding ones.
Yes.
So there are evolutions that will change the individual string winding.
String of the minimal one. Eventually, all strings of higher winding will split into minimal windings.
That is the case of the minimal model. It's not necessary for the more complicated one.
Okay.
And the minimal model does not produce the rest
Okay,
of it.
this I don't understand, I'm sorry.
Okay. May I ask you some kind of sidewise question? Maybe it's only me who sees this because it's every time you are kind of moving slides that I have this symbol of Munich 1972 Olympiad. You know, is it accidental?
Wait, what? What?
I know. Look, it's maybe it comes from some Janet Sobol string screen, but what now, for example, I see this, right? I see this Olympiad symbol of 1972 with the flame, whatever. And I wonder, it's probably something not related.
I'm sorry, I'm not seeing that.
Okay.
We're very
I'm sorry. Okay, thanks for the talk anyway.
okay. Thank you. Wait.
Somebody else in the background.
Oh.
Somebody else was watching.
Yeah.
It's somebody else's icon.
Yeah.
So all of these are happening below QCD scale, right? That's what you said. You cannot.
No, the cosmic string.
That's
I need to dynamically.
But it seems though, another way to look at what you've been arguing is that pre-inflationary axion direction and simpler. by far.
Yeah, you just,
I don't need any of this, right?
you have so you have a lower inflation scale to avoid the isopropyl problem.
Is that the only way to avoid?
Because in the pre-inflation, whatever you produce there, corner walls, domain walls. They're inflated away.
Yeah.
So forget about it.
Exactly.
You produce this.
There are dark matter. I just cannot predict what the mass. But you also have.
Yeah, see, I see.
It's bigger than one.
No, because the question of the not being able to thing with any dark matter model is something to Simpson supersymmetry, you could say, well, we have the right dark matter density, I needed to have some of this mass. And I don't know how to predict that any other way. It's the same thing. It's just that, you know, the mass is whatever it is, we get a value of omega that we measure and measure it elsewhere. I don't see this problem. I guess the icing curvature.
Oh, we cannot predict the Anything else? It already becomes a well, right? No, if you say we cannot keep that, or that, then you set yourself a goal, basically to at the level of something like what? Because, okay, we can predict cosmology. We do live, we have physics now, we I cannot predict the condition. Previously, never ever Galileo was not thought how to predict. You only thought about what you saw, what people measure. You don't build the same. Now people are much more ambitious. Maybe that's okay to become more ambitious because we advanced very much further compared to Newton, let's say. But when we ask such questions, you should understand that principle we may never even, I don't know, 1,000 years, but it existed in principle, such questions are not necessarily answerable. Especially if it depends on physics at the Planck scale. Apart from some residual traces of what happens at the Planck scale, we have no way to make an experiment at the Planck scale, right? So we have to observe only whatever little things we have. So, okay. For young people, it's very good.
They hit.
Maybe something but in the cosmology, the last we understood, but there are other things of similar nature which disorders. Okay, thank you anyway.
What is the solution? I took that time.
Oh,
Yeah, so this is, I put really assumption.
It's just that the first string possible actually more on the one to one. I think the middle of not I think.
Will ask, I will write. We put on the screen the first page and I made a picture of you.
Oh.
On the background of the first page.
Oh, yeah. With my name.
Well, sometimes I forget, but almost every time. You know, you stand either at the center or because otherwise there is a shadow which goes right.
Sorry, he wants the title slide. Yeah.
Okay, so I'll what? Like this. Thank you.
Thank you.
We can turn off the.
Yeah.
You're focusing on.
Wait.
You're focus flexible. Like there are other
Yeah.
models where you
Oh,
don't.
like.
Have- like,